Configuration of aluminum.
This one is, should wipe it off earlier. Okay, so we're looking for the electron configuration of aluminum. Do you remember this from earlier? What is the electron configuration of aluminum? Oh, and that's the question is over here. Do you remember that? So this is the thing that's like 1s2. Do you remember that? Okay. Do you know what's next? Good. 2s2. 2p, and then it goes to 6. Then 3s squared, 3s2, and last thing is 3p. How many p electrons for aluminum?
3p, right?
3p, and there's just 1.
Yeah.
Yep.
Do we have to put the 1?
You have to put the 1 in this case. This is like the only case where we use, if we have 1, we'll put a 1. All right, so I want to show you really quick. So this is the energy level, right? This is the orbital. This is the number of electrons in that orbital. If you use the periodic table, the shape of the periodic table can help you with the electron configuration. Okay. So if we go to the periodic table, P table, and then if we look at, so hydrogen has 1 electron. It's in the 1s. So this is the energy level. These two, let's do this actually. If you look at the periodic table like this, I just want it to be perfect right there. So hydrogen has 1s electron. Helium has 2 1s electrons. Okay, and then we jump down to the 2s orbital. So there's 2 electrons in the 2s orbital. And then we go over here. Oh, where's the mouse? This one. These are the 2p electrons. This is where they live. Does that make sense? And then we go down. Let's see if this one's working yet. To the 3s. Oh, so these are the 3s orbitals, the 3s electrons. And then we're here at aluminum. This is another p block. So depending on where we are on the periodic table, that can help us know how many electrons we have and where they are. So the shape of the periodic table can help you with this question. Okay. You will only be asked to go up through argon. So for this question, if this is something that you really struggle with, I would write down the electron configuration for argon, and then you can get any of them before that from the argon. Does that make sense? So if that's something that you're struggling with, that's what I would do for the final. Okay, or you can just use the periodic table. If that makes sense to you, then you might not have to write that on your periodic table. Okay. All right, the next thing that I would like to do is I would like to go over Lab 4, the Lab 4 equations. So go ahead and pull out your Lab 4. So that's the, we did, basically it was like a chemical reactions lab. So let me see. So we're going to go over a few of these things. I only have one copy, so let's see how that goes. Okay, are we ready? We have our lab 4 out. Okay, so hopefully you have already done the observations. So this is the most important thing that you did in the lab. You made your observations. And then most of the other things you can do outside of the lab. So the blanks are for balancing, right? So if we have this equation, then we're going to need 2 oxygen. So we put a 2 in front of there. So we have 2 oxygens on both sides. That means we have 2 magnesiums. So we'll have 2 magnesiums on both sides. So that's what those lines are for. You're supposed to balance just like in chapter 5. Okay. And then write in words what happened. So using the correct names for these things. So what happened in this reaction? How would you describe in words this chemical equation? Good. Perfect. Magnesium and oxygen combine to form, what's this?
Magnesium oxide.
Magnesium oxide. Good. My last class was having a hard time with prefixes. We do not use prefixes if it's covalent, or excuse me, ionic. These are all going to be ionic. Don't use prefixes. So perfect, magnesium oxide. The next one is same thing. So you're going to balance it. I'm going to let you do that outside and then write in words. What you've got magnesium oxide plus water gives you, what's this one?
Hydroxide.
Good. So you got magnesium hydroxide. Perfect. Good. Okay, this one's a little bit different because it's a transition metal. So we need the Roman numeral in the name. So what's the charge on the copper? Yes, it's 2. So the name of this would be copper 2. Good. Perfect. So if it's a transition metal, it can form multiple charges. So we need to list the charge that it is in this compound. This compound has an oxygen, so we know oxygen is always a 2- charge. Copper here has to balance the 2- charge, so that's why copper is a 2+ in this compound. So make sure you use the correct names for these compounds. All right, scoot down. So I think you guys can do the rest of those. Those ones. Got them. Let's see. The next thing is the reactions. Let's look at the part 2 box. So I wrote on mine already, so I'm just gonna make some boxes and we'll kind of go like this. Okay, and we can do that here. Okay, so I don't know if you can see this on mine, but hopefully you can see on yours. The top thing says description of the precipitate. So hopefully you saw something solid. If you didn't, write what you observed, okay? I know some of our reactions didn't work as well as I was hoping. So that's the first box. You're supposed to write what you observed. Okay, the next box is the formula of the precipitates, but it's more helpful to do the next one first. So we're going to write the balanced equation first. Okay, so if we look up here, we have all of the words that we need to make our balanced equation. So this is saying we have nickel 2 chloride. So nickel is a 2+ charge because it tells me that, 2+. Chloride is a 1- charge. Hopefully we just know that. We can look at our periodic table to remind us that. So then we need to write the balance formula for this chemical. So how many chlorines and how many nickels do we have to have if we have a nickel 2 chloride compound? Or the other way we can do this is we can say, oh, we need 2 chlorines for 1 nickel. So this is going to be nickel 2 chloride. So this is like chapter 3 stuff, but we're just revisiting it, and we actually did something in the lab with it. So that's the first part of our balanced chemical equation. So this is like showing my work figuring out the formula for nickel chloride. So I am going to put nickel chloride. That's one of my compounds. It was dissolved in water. So all of my chemical equations need a phase. So if it's dissolved in water, then I need to put that it's in the aqueous phase. That's the AQ. Have you ever seen that? Oh, thank you. Okay. So if we have nickel 2 chloride is added to sodium carbonate. So I'm just reading the sentence on the top of my box. So I need to know the formula for sodium carbonate. So I'm just going to put it up here. Sodium is +1. Do you guys know the formula for carbonate? That was one of the polyatomic ions you had to memorize from chapter 3. Polyatomic ions, carbonate. It's also in the lab. Okay. Carbonate is CO3 2-. Does that sound familiar? Kind of? Okay. So now we have a plus charge and a 2- charge. So we need to figure out the correct formula if we have a sodium and a carbonate together. They will form, we'll have 2 sodiums for 1 carbonate. So it's going to be Na2CO3. And this also started out as a dissolved sample. So we're going to say that's aqueous. So Na2CO3 aqueous. And then our sentence says to produce, so that's going to be to produce an arrow. Okay, to produce. And then I'm running out of space, so I'm going to put it down here. To produce what? What are we going to produce? It says we produced nickel 2 carbonate and sodium chloride. So I'm going to erase this one. I'm just giving myself some more space here. We have nickel with a 2+ charge. And we have carbonate, CO3 2-. So what would our formula be for nickel carbonate? Yep, each one, perfect, because they both have a 2- charge. That's perfect. So NiCO3. So to produce, we got nickel carbonate plus, so it says and sodium chloride. What's the formula for sodium chloride?
SCO.
So, and sodium is Na. Yeah. Sodium is a weird one. Na. You got it. Yeah, you're good. NaCl. Oh, and then we have to decide which of these, what phase are these? Okay. So we need to look on the instruction sheet. Do you guys have instructions? I think my other class. I have 1, 2 instruction sheets. Do you have any instruction sheets? Okay, you have some instruction sheets. Well, let me try to get one per table. You're going to look at, do you have instructions? Look at the table in the back of the instruction. This one, right into that. Yeah. Oh, you don't have instructions. You guys have instructions? Can you share? I put like one on each table because they are missing. Okay, the other place you can look is on the Weber State website for the instruction page. All right, so now do I have one? Oh, I have one more. Do you want that one? Okay. So we have to figure out which one is a solid and which one is dissolved in liquid. Oh, that's wrong. So this is lab 4. This is in the instructions. Okay, so we have this table. It's a little bit small up here, but hopefully you can see one. You have access to one on the back of the instructions. So you need to go through and you need to figure out. So the first one is nickel 2+. So if I look down here, let's see if we can make it bigger. So if I look here, I've got nickel 2+. The green means that it's soluble, that it's going to be in the aqueous phase. So if it's nickel chloride, it will be soluble. Okay. So we have nickel carbonate. So let's scroll over. Oh, very good. So hopefully this is easier on your paper. So we've got nickel 2+. That's this one. And then I'm going to look over and find carbonate. So nickel carbonate says no, it's not soluble. So that's going to be our solid. So on your equation, you need to write nickel carbonate is a solid. That's the phase. So I'm going to write it here. We also need to check sodium chloride. So find sodium as the cation. So sodium is Na. Chloride is Cl-. Sodium chloride is soluble, yes. So that one would be aqueous. Okay. All right, so let's go back to our, so this one is a solid based on that chart. This one is aqueous based on that chart. Okay, so that is our equation. Then we need to see if it has to be balanced. Is this balanced? So on this side, we have 2 chlorines. So on this side, we need 2 chlorines. This side, we have 2 sodiums. Now this side, we have 2 chlorines. So I just need a 2 in front of the sodium chloride, and that will balance the equation. So that's the first part of this. And then in the precipitate that's formed, well, we formed this nickel carbonate. So that's going to be our precipitate that's formed. And we know that's the solid because of the chart that we have. Okay, question so far. So far, let me go back to this box. We are to here. We have, hopefully, you have to do the observations in the lab. And then you have your precipitate, nickel carbonate, nickel 2 carbonate, and then you have your balanced chemical equation. Okay, the next thing is the what is it called? The complete ionic equation. So that's where anything that's aqueous, we're going to show as its ion. So we'll use this, and I'll do the same thing that I did here. So the complete ionic equation, everything that's aqueous, I'm going to split into its pieces. So here I have nickel. Nickel is a 2+ charge, so I'm just going to break that into its ions. Ni 2+, okay, that's coming from this. And then chlorine is a -1 charge. Oh, also nickel 2+ is aqueous, so make sure you put your phases. Plus this ion, Cl-, but there's 2, so that subscript I'm going to put in the front. I'm going to say, oh, I have 2 chlorines. Okay, that's also aqueous. That goes to, add, I also have this one. I have sodium carbonate, that's aqueous. So I need 2 NAs, Na pluses. So I'm just breaking them into their ions and writing them. Everything that's aqueous, I'm breaking it up. And then we decided carbonate, oh, this is also aqueous. So make sure you're putting the phases. That's something they asked me to look for. So I'm telling you now, make sure you put all the phases. Carbonate is here. That's CO3 2 minus. There's only one of those, so that's also aqueous. Okay, I'm going to run out of space, so I'm going to put on the other side of the arrow, I'm going to put as a second level. Okay, and then I have this one. This one didn't break into pieces because it's solid. So if it's a solid or a gas, it doesn't become its ionic pieces. Okay, so this one I'm just going to write out the same as I had before. NiCO3, that's a solid. And the next thing is aqueous, so it's going to break into its pieces. And I have 2 sodiums and I have 2 chlorines. So 2 Na pluses, that's aqueous. And then the chlorine breaks off, 2 Cl minus, which is also aqueous. Oh. Okay, so that is my complete ionic equation. That's like the giantest thing that we have to write. Okay. Are you good okay so far? Questions where any of that came from? And it's still balanced. I have the same numbers of things on both sides. Are you okay? Okay. And then the net ionic equation is anything that happens on the left and it's the same thing on the right, we can drop it out. That's not actually doing anything. It's just a spectator ion. So if it shows up on both sides, we're going to drop it out. So again, mine is like this is the left side, this is the right side. So I'm going to look through and see, is there anything on the left that also appears on the right? 2 Na is good. So this one matches this side. So for the net ionic equation, I'm going to cancel those out. So they're not really doing anything. They're just spectating. They're like just watching the rest of them react. So these aren't doing anything. So my complete ionic equation, or excuse me, this is the complete. My net ionic equation is just the ions and solids that are participating in the reaction. So that would be nickel is doing something, nickel 2+, which is in the aqueous phase. And that's combining with carbonate, which is also in the aqueous phase, and they're combining to form nickel carbonate. Okay, so that's and it's also still balanced, and I have my phases. That's the net ionic equation. Okay, so that's the process. I'm going to, at the end of class, we'll take some work time and you can finish that part. We're going to go over some of the post-lab questions, but that is the process. Okay, so that's what that one looks like. You'll have your just explanation, your solid balance total equation. Yes, your net a complete ionic equation, net ionic equation. Okay. Aluminum is not on the back page. So aluminum, you will have to go to, I keep looking at the wrong, this website. Or you can just look it up, like Google solubility chart for aluminum. Anyway, so this one is the one for aluminum. The one that's on the back page from Alex doesn't have aluminum. Okay. All right, so let's also talk about the post-lab questions. Let's talk about a few of those. So the first one I want to talk about is number 4. So look at post-lab question number 4. It says, in the reaction of magnesium and oxygen gas, a considerable amount of energy was released. This is an example of an exothermic reaction. From this evidence, what can you conclude about the energy stored in the reactants compared to the energy source in the product? So the first thing is exothermic. It says it's exothermic. So what does it mean if a reaction is exothermic? What is happening? What is the energy doing? Good. Yes. So that's the first thing that they want you to explain is that exothermic means energy is released. Okay, the other thing it's asking about is the energy level relating to the products and the reactants. So I think it's helpful to look at a graph of exo. So what does a graph for exo look like? How do we know it's exo? So if my reactants are here, where should the products be? Lower, good. So exo would be like this, something like this. Okay, and this is, I just said that this is our reactants, and this is our products. What is the axis labeled over here?
Energy.
Yeah, yep, good, energy. So that part in the question is asking about how do the energy levels relate between the products and the reactants for an exothermic reaction. The graph will help you explain that. So what is going on? How do they relate?
There's less energy in the products.
Perfect. Yeah, there's less energy in the products than the reactants. So that's what it's getting at, is that when you have an exothermic reaction and you're releasing energy, those products are really stable. There's lower energy in the products. Okay, so think about that graph as you're explaining that question. Okay, number 5 also tells us that there is an exothermic, so that says there's some other exothermic reactions. Were there any other reactions that released energy? And we would know that because it would feel warm. Were there any other reactions that felt warm when you mix things together? So look through that. Let's look at it's saying this time write the term energy on the appropriate side. So let's look at, it tells us that this one for sure was exothermic. So let's do that one together. So it says write the balance equation. So we know that the first equation, or the first reaction, was we had magnesium metal plus oxygen gas gave us magnesium oxide. I don't know why I didn't put a G. Okay. And then this one has a 2. This one has a 2. So that's the balance one. This one was a solid. This one was a gas. This one was also a solid. Okay. And then it's saying this time write the term plus energy on the appropriate side. So if it's exothermic, where does the plus energy go? Energy, where should it go? So we did heat this one up. So this one, we did use heat as kind of a reactant, but it's getting at that it's exothermic. So if it's exothermic, do you remember this one was like really bright? It like blinded you if you looked at it. So that's a product. So energy in this reaction was a product. Oops, I'm ready. Energy. So anytime we have an exothermic reaction, heat is a product. So we can either get light out, like this reaction, or we could get heat out. That would be energy as a product. Okay, so that's what it wants you to do. So look for any other ones that were feeling warm or gave off. I don't think any other ones gave off light. So, but, oh, maybe you could, the isopropanol, right? That one gave off light when you burned it. So that one, you could use that one. Okay. Let's see, what else do we need to talk about? Then we need to look at the post-lab questions for the second part. So this one. Okay, so the first thing we're going to do is we're going to look up a water company. So on the instructions page, oh, I keep looking at the wrong Google. It has this website here, ewg.org/tapwater. So this rates how our water quality is. So what you're going to do is you're going to put your zip code in. And then you're going to find a water company, a water supply company. So you can click whatever one you want to. I'm going to click on this Washington Terrace one because that's where the school is. But you can click on whatever one, okay? So then the question is asking, Name of water company. So this one would be, I need to move that over here so I don't get confused. This one was Washington Paris City Water System. You can look at a different one if you want, that's fine. And then it says 11 exceed EWG health guidelines. So it says legal does not necessarily equal safe. So we have some different definitions of what is acceptable in our water. So then what do? We look at, if we scroll down, it says contaminants detected. So let's go back to our questions. I think I'm in the wrong one. It might be easier to look at, we'll just go back here. So we're looking for nitrate. Which section did nitrate appear in? Is it exceeded or other? So if I go back to that website. Oh, that's not the website. Thanks. So look for nitrate. Is it an exceeded? You see nitrate? Where is nitrate? Nitrate says it's exceeded guidelines. So if we go back to this, that one's exceeded. Okay, and then if we look in other, we can also see the other contaminants that are detected. So these are some other ones that are detected. So then we can look at like the legal limit versus what is actually tested in the water. And then they also have like guidelines. So legal versus guidelines is different. And this one's just based on guidelines, which is stricter, I think, generally than the legal limit. Okay, so then the next question said, could a flocking agent be designed to precipitate nitrate? So remember we talked at the beginning, we talked like very briefly about a flocking agent, and it needs a cation and an anion. And then one of them is going to make the thing that you're looking to precipitate, and then you can filter it out if it will precipitate. So we need to go back to our chart, if we can find it, and look for nitrate. So nitrate is an anion, so it should be up here. Okay, here it is, nitrate. And then we look down this chart, or you can look at your chart. Is there anything that will make nitrate precipitate out? Is there anything that will make nitrate a solid in solution? No, everything is aqueous on this one, and I think on your chart too. So would we be able to use a flocking agent to precipitate nitrate? No, we can't. And then explain why. So it looks like from this table, there is no ions that will precipitate nitrate. Nothing, everything that we have on this chart will leave nitrate in the aqueous phase. It's going to be dissolved. Everything that we add is not going to precipitate nitrate. So therefore, we can't make a flocking agent that's going to make nitrate precipitate. So that nitrate's a little bit tricky. Okay, so the next question is asking, well, if you can't make nitrate a flocking agent for nitrate, let's pick a different ion. So pick a different ion that you want to precipitate. So look back at this chart, and we can look at other, we can look at exceeded. So, and also it's going to be easier if you find something that is on the chart. So I don't think arsenic is on the chart. No. So we can look at other. Let's see, barium, boron. Maybe we could look at fluoride. Okay, so we could look at fluoride. Maybe we want to make fluoride precipitate. So if we wanted, so the other class we picked barium. But I want to try another one. So you can pick anything that's in here that would be on this chart. So I'm picking fluoride right now. Is there anything that would make fluoride precipitate? So here's fluoride. I don't think I can just drag down. But it looks like aluminum would make fluoride precipitate, barium would make fluoride precipitate, calcium would make fluoride precipitate, cobalt, iron 2, oh that says copper 2, copper 2, lead 2, we probably wouldn't want to add lead to our water system, so let's not do that one. Magnesium. Okay, so does that make sense? You're picking something on the chart and you're saying, oh, let's go back here. Identify, oh, it says a cation. Well, I picked an anion. So let's go back. So I think the only cation that we can precipitate with our list is barium. So let's go back to our chart. So if we wanted to precipitate barium, so we would pick barium as our cation that we want to precipitate. And then the only, let's see, so then we look through this row. Is there anything that would make barium precipitate? So it looks like it would precipitate with carbonate, fluoride, phosphate, sulfate, sulfide, sulfite. So which anion would you recommend using as part of your flocking agent? So you're going to pick something that would make barium precipitate. Does that make sense? Okay. And then the other thing you have to do is you have to recommend the flocking agent that you would use. So remember, we're picking something that has a cation and an anion, so it's an ionic compound. We can't just add a negatively charged thing and precipitate because the negatively charged thing won't go, it doesn't exist as a negative thing by itself. You have to have that charge balance cation. So we need to go back to our chart and we need to find something some ion that will precipitate barium but will be soluble when we add it to the solution. So for example, if I want to precipitate barium, maybe I want to pick carbonate. Well, I can't just add carbonate. I need to add an ionic compound. So maybe I'm going to pick this aqueous ammonium carbonate, because if I add ammonium carbonate, it's going to break into its ions and then the carbonate can go after the barium. Does that make sense? Okay, and then the barium carbonate will precipitate out. So I have to find my flocking agent has to be something that has the anion will precipitate out barium or another cation, but the form that I add as the flocking agent has to be able to be soluble. It has to be able to break apart in solution. So one example would be if I add ammonium carbonate, then the carbonate can precipitate with the barium. Another example would be, so I need something that's soluble or solid with barium, so maybe phosphate. And then what cation plus phosphate? Let's find another one. So it says lithium. Is that this one? So lithium phosphate, if I add that to solution, the lithium and phosphate will break apart. The phosphate can go after the barium and precipitate that out, and then I could filter the barium out of my water. Does that make sense? So also when you were doing this, like if you were really doing this, you would think about like, do I want to add lithium to my water? Or is there another thing that I could add that would precipitate out the lithium that I could filter that out? Okay. All right, so kind of interesting. Real world application. Okay, do you have questions on that? Okay, all right, we're gonna stop there. And I was going to try to get Lab 5 set up, but I have a meeting during my prep today, and I don't think I'm gonna be able to set up Lab 5 by next week. So I think we're just gonna trade. So we're gonna have Lab 7, or we're gonna talk about Chapter 7 today. Then we're gonna talk about Chapter 7 next week also, because I just don't have time to set up Lab 5. I'm a little bit behind, so that's kind of where we are. I think, so what we'll do is we'll do Chapter 7 today, we'll do Chapter 7 Tuesday, then we'll come back and do more Chapter 7, then we'll do our lab towards the end of the week. So, I thought I had more time, but I do not, so. Okay, the next thing we're gonna do is talk a little bit about Chapter 7. So we've got about 35 minutes left. So, let me pull up I need my slides up, so let me do that. Yeah. Okay, we are talking about, mostly this chapter is about gases and the relationship between different gases. So we just need to do like a super brief overview of what is pressure. So pressure is a force over an area. So I like this picture because if we have a force over a big area versus a force over a little area, this will give us more pressure than this one. Okay. And also, pressure is when gas particles are colliding with their container. So if you imagine, I don't have a balloon, but if we have a balloon, then the gas particles hitting the sides of that balloon are what is giving the balloon its pressure. Or think of like your tire on your car. The gas particles are exerting a pressure on the tire wall. The more collisions, the higher the pressure. Okay? And then we have some units. Let's go into Alex and look at those units. We're going to actually do a conversion problem. Just like we did with chapter 6 and energy, we will also do a conversion problem in Alex. And then there. So this is the first one we're going to go over, interconverting pressure and torque. So in Alex, if you go to the data, and then you go to the fourth topic, or the fourth data topic down, conversion factors for non-SI units, that has, if we scroll to this big section down here, that has these conversions listed. I would probably still put these on my note card. So I'm going to tell you which ones I will put on my note card. For this topic, I will use the torr and the millimeters of mercury. That's the ones that we need. So let me pull up my camera again. Let's fit this on here. And works very good. Okay, so let's see. If I have 1 atmosphere, that's the same as 760 torr. If I have 1 atmosphere, that's the same as 760 millimeters of mercury. So what do we notice about these two? Anything? Hopefully you're noticing that's the same number, right? So that tells me that 1 torr is the same as 1 millimeter of mercury. So when I do this problem and I need something in torr and I have it in millimeters of mercury, they're going to be the same. Can you wait till Emma comes back?
Yes.
Okay, thank you. Okay, so let's do this problem. I need to close this. Let's close that. So this one says, we have the vapor pressure of water at 80 degrees is 355 torr. So somebody pointed out, this is just like some information. We don't need that at all in this problem. All we're doing is we're converting the pressure to these other two pressures, okay? This has 3 significant digits, so these will. This is one on the test that you won't get you'll have to know how to figure out significant digits, okay? This one's easy, you just look at, it says 3, you're gonna use 3. So we have this number, 355 torr. We need to convert that to atmosphere and millimeters of mercury. So this one's easy. If it's in torr, then it's the same number in millimeters of mercury. So I can just put that in here, 355, oops, decimal. Okay, so that one's easy. They're like interchangeable. Very good. Okay, so then the other one. We need to get to atmosphere. We have torr. So I'm going to use this one because that's relating atmosphere and torr. I'm going to put the atmosphere part on the top. I'm going to put the torr on the bottom. Because I need the torr to cancel out and I need the atmosphere at the end. So then I'm going to use my calculator. Let's see if we can find it over here. Here it is. And I'm going to put in there 355 divided by 760. And that will give me the pressure in atmosphere. So that's 0.467 atmospheres. Move this back over here. Okay, questions on that? Do you want to do another one of these? Okay, let's do another one. All right, so there's some like irrelevant information. The atmospheric pressure on top of Mount Everest with an elevation of this is 250 torr. So this is the number we want. So I'm going to write that number down. So always start with the given value, 250 torr. And we need to calculate this in millimeters of mercury and atmosphere. So what would it be in millimeters of mercury? That one's 1 to 1, so it's going to be the same. 250 decimal. And then we need to calculate it in atmospheres. So we are trying to find atmospheres. We know that 1 atmosphere is the same as 760 torr. So that torr will cancel out. So it's 250 times 1 divided by 760. $250 divided by 760 will give us this, and this one has 3 sig figs, so this will have 3 sig figs. 0.3. Oh, 289. So I'm going to have to round this up to 30. Do you agree with that? There's a 9 there, so I need this. Oh, no, I just need to make that a 9. Okay, sorry. 2.29. Yeah, that will just round up to a 9. Okay. Sometimes the 9s trick me. Okay. How are we doing on that one? Are you okay? Yes. Oh, yes. Let's try another one. So we'll write down the atmospheres. Oh, this one's little. 0.00. Is that 3 zeros? 314. That's in atmospheres. And we're trying to find that. Let's do this, the top one. We're trying to find that in millimeters of mercury and torr. We'll do millimeters of mercury first. So we need atmospheres to go on the bottom this time because we needed that to cancel. So for 1 atmosphere, we have 760 millimeters of mercury. So atmospheres cancels, we'll get millimeters of mercury. So then we'll take this times by 760 to get our answer. 0.0003. Oops, that's a 2. 34. Oh, 314. Times by 760. So then we need, this has 3 significant digits, so this one has to have 3. And then this has a 6, so we need to round this up to a 9. So 0.239 for this one. Oops. 239. That's millimeters of mercury. So how are we going to find the torr one? They're the same. Yeah, good. So if I have it in millimeters of mercury, that's the same value for torr. So okay. Yes. Yes, that is okay. Yep. So if I wanted to do that, I have that magic button on my calculator. And yeah, that could be, and then you just make sure, same thing, you'd have 3 significant digits. Yep, that's fine. Yes, and I think there are some that get really small. That's fine. Okay, other questions on this one? Okay, all right. For a few minutes, I would like to play with a PhET lab. So the lab is linked in the slides. Or if you go to, I think it will come up if you do PhET simulation, gas properties. That should pull it up. We're just gonna try to build like an understanding of what's going on here. So we're gonna use ideal gas. So an ideal gas is like something that doesn't interact with the molecules, don't stick together at all. So I'm gonna pick ideal. Okay, and then we're gonna use the definitions here. Let's see. So pressure, we talked about pressure is the number of collisions. So if we have more collisions, we're going to have a greater pressures. Then we're going to look at what's happening to the temperature. So let's say hold constant. Let's say our volume is constant for now. Okay, so I'm going to put into my box, this is my box of gas, I'm going to put some gas. So I just added some molecules, okay, and I'm going to stop adding molecules, atoms, I think they're atoms, and I can see my pressure. Can you see my pressure kind of fluctuating here? So let's see what happens if I add heat. What's happening to the system? What are you noticing? So I'm noticing my thermometer is going to break. So that's telling me if I increase the temperature, so let's write that. So if we have our temperature and we increase the temperature, what happens to pressure? What did you see? So this is our pressure. What's happening to the system? Let's see. If we increase our temperature, can we reset that? Reset this.
Pressure goes up.
Yes. So if we increase the temperature, the pressure goes up. Okay. What happens to the speed of the molecules? Let's try, what happens if we cool it down? What's happening? So the particles are getting slower. So if we decrease the speed of the molecules, we're getting less pressure, we're decreasing the temperature, okay? So, okay, let's look at what happens if we're gonna keep the temperature the same. And we're going to let's do this. This is what I want to do. Let the volume get bigger or smaller. So what happens if we increase the temperature? What happens to the volume? So if we have the temperature and we increase the temperature, what happens to the volume if it can move? It increases. Good. Yep. Good. What happens if we decrease the temperature and we're keeping the pressure the same? So the pressure is the same, but we're decreasing the temperature. So we need a smaller volume to keep the pressure the same. So if the temperature goes up and the volume goes up, that's if the pressure is the same. Pressure. I think that's not how I spell pressure. I don't know how to spell pressure right now. Okay. Pressure is constant. Okay. What else do we need? Pressure, volume. Let's see what happens if we keep the pressure the same. So that's locked in. But we're going to change the temperature. Or the temperature is going to go up or down. Is that what we're doing? Oh, the temperature. Oh. Held constant pressure. So this is what's happening. We're keeping the temperature the same. Oh, no, we're not. We're keeping the pressure the same, but the temperature can vary. So if we open the system more, it has to heat up to keep the same pressure. So the temperature has to increase to keep the molecules moving in a bigger space to keep the same pressure. Okay. If we make our space smaller and we want to keep the same pressure, our molecules have to move slower. It has to get a smaller temperature so that we have the same number of collisions to keep our pressure the same. Okay. All right, so let's go back to Alex, and we're going to do one of the problems called Boyles Law. And we're going to try this box. Here it is. Understanding Boyles Law. So for these problems, we can use this box. We're going to try this. Let me try to put it up here. Okay, so this is Boyles Law or the piston problem. If you have a piston problem, you're going to think like this. So we're going to draw this table and see if this helps us. So we've got P, V, N, T, and N. So this is what can change. The pressure, that's the number of collisions. Temperature is the speed, basically the speed of the particles. V is the space, the volume, the space that the molecules have to move. This is also called the volume. Okay, and then N is the number of particles. Okay. All right, so in this problem, we have a cylinder that is filled with gas, and we put a piston in it. The initial pressure is measured to be 141 kilopascals. So we're going to draw this table with our pressure, volume, temperature, and number of particles. We're going to see what happens. So this is our initial values. This is our final values, and then this is the expected, what do we expect to happen? So this one we have a pressure of 141 kilopascals. That's initially. And then it says the piston is now pulled up. So they pulled up the piston. So kind of like in here, if we pull up the piston, we're like opening the box. Okay. So they opened the box. Oh, and what happened? Our temperature was constant. So that's like this. So if we have our system and we open the box, what's going to happen to our pressure? Should decrease. Okay, good. So that would be our expected, what we expect to happen. Okay, the piston is pulled up, expanding the gas until the gas has a final volume of 38. Oh, I missed the initial volume. Initial volume is 10. I missed that. Okay, so it didn't say anything about the temperature, so the temperature didn't change. It didn't say anything about adding or changing the number of particles that we have, so those are the same, okay? So we're just looking at pressure and volume. So if we increase the volume, what did we decide is going to happen to the pressure?
Decrease.
Yes, so we're going here to here, so we expect this to increase. The pressure should increase because our volume decreased. Do we agree with that? Or excuse me, increased. Our volume increased, so our pressure should increase. Do you agree with that? Okay, so we're going to take this number. This is our pressure, 141 kilopascals. And then these are the two numbers that we can use. We're going to make a fraction with these two numbers and make our pressure go up. So what are we going to put here with these two numbers? What should go on the top to make it get bigger? Yes, 38. And the other one has to go on the bottom. And then liters will cancel out. So we just figured out what the pressure should be. And then we need our calculator to type that in. Can we get a calculator? I wish that I didn't have to open my window so big to get the calculator to show up. So 141 times 38 divided by 10. This is our final pressure. And does that make sense? Did it go up? Yes, it went up. So that makes sense. Okay. And we need 3 significant digits. They all have 3. So 536 decimal. Okay. My answer is incorrect. Very good.
What's wrong with you?
Did I put the wrong number? 141. Did I type it in wrong? Maybe I typed it in wrong. I'm trying something new. The person from Weaver State came yesterday, and I'm trying to try her new thing, but I'm not sure that is working for me.
I think you need to flip 38 and 10. That's my flip.
Oh, do we have it upside down?
I think the energy was supposed to decrease, so we should put the smallest one on top, right?
Oh, so this is the expected.
Oh yeah, expected.
Oh, okay, so we have it backwards? So this should decrease? Thanks, Ian. Wow. So if our volume is increasing, oh yes, okay, if the volume increases, if we have more space, there's going to be less collisions. So that should decrease. Okay, thank you. Yes, that makes sense. So if we want it to go down, then we need this number to be on top. Yes, you got it. Thank you. So then that would be 38. So we'll just switch those. Okay, so that would be 37, and that goes down, so that's good. 37.1, let's try that. Okay, great. All right, do you want to try another one of these? We have about 10 minutes. Okay, let's do another one. Okay, so this one, we have our values. This one again, we have a piston that starts with 10 liters. So that's our initial volume, 10 liters. And the initial pressure of the gas is 217 kPa. It says we push the piston down, so we're gonna smash the piston. So think about, have you ever held like an empty syringe on your thumb and you push it down? What happens to the pressure? So we should expect that this one, the pressure should go up if our volume is going down. So our volume is going down, our pressure should go up. So this is, we're supposed to be trying to build an intuition about what's happening. So if we are decreasing the volume, our pressure should go up. Okay, so now I think this will work. Okay, so then we'll take our pressure. We need it to go up, so we're going to put the big number on the top. Liters cancels out, we'll get kilopascals. That's what our answer is asking for. And then we'll type that in to our calculator. So 217 times by 10 divided by 4. So we should get a bigger number. They all have 3 significant digits, so we will put 3 significant digits in our answer. 529 with a decimal place.
Does it always only include the left 2 columns, never the right 2?
For this problem, yes. For Boyles Law, we'll only use pressure and volume. That's true. For the piston problem, for Boyles Law, yes. Okay, do you want to do one more of these, or do you want to work for like the last 7 minutes? You want some work time? Okay, all right. We'll continue on chapter 7 next time also.